for us. We always want to measure flow. We especially want to measure flow accurately because quite often flow involves billing. And billing is something that people feel kind of serious about. There's two types of flow measurement. There's volumetric flow measurement. This is where we're measuring volumes. We're measuring liters per second or cubic meters per second or something per minute. We're measuring volumes. And there's mass flow. Mass flow is where instead of measuring liters per minute, we're measuring kilograms per minute or kilograms per second or kilograms per hour. Generally speaking, when we're measuring volumes, which is liters or cubic meters, we're actually measuring velocity. We're measuring the velocity of the stuff going past. And from the velocity, we're calculating the volumes. There's a few different types of fluid that we're measuring. We measure gases. Now, problem with gases is that they expand and contract. That can be really troublesome when we're selling things by litres, because 1 litre might be quite a small amount when it's hot, but 1 litre might be a large amount when it's cold. We also measure liquids. Things that liquids do is liquids tend to flow to the bottom of the container. Liquids are not very compressible. Quite often in WA, the other thing we're measuring is liquids with sediments in. Mineral sands, sludges, that sort of thing. They have got particular problems because the sediments and the denser particles tend to settle to the bottom. When we're looking at the way flow travels, especially the way flow travels in pipes, we have to be aware that at the actual wall of the pipe, at the actual pipe wall, the velocity is 0. The velocity next to a stationary surface is always 0. With a pipe, most of the flow happens in the middle of the pipe. There was a chap called Oswald Reynolds, and Oswald Reynolds came up with a number which expressed the different ways that liquid would flow or fluid would flow in things like pipes. And Oswald Reynolds came up with this number. And Reynolds' number relates to things like the density. Rho is the density. The velocity, the diameter of the pipe, and something called the dynamic viscosity of the fluid. Now, generally speaking here, we're talking about probably liquids. Now, you should be aware that there is something called a dynamic viscosity and a static viscosity. To let you know the difference, if you take a bottle of ketchup out of the cupboard, if it's been sitting in the cupboard for a week, it's very, very thick. It has a high static viscosity. But if you shake it up, it thins out. And it has a different dynamic viscosity. Dynamic means moving. Lots of liquids behave this way. Lots of liquids have a totally different static viscosity than dynamic viscosity. So, moving along then. Reynolds number. Reynolds number comes up with these strange numbers, really, when you do Reynolds equation. If Reynolds equation comes up with a number that is less than 2000, what this means is that all the fluid is flowing, is the pipe, all the fluid is flowing in layers. So on the outside it's going at 0, and then the next bit is going a bit faster, the next bit's going a bit faster, the next bit's going a bit faster, and then it comes back out again. It's flowing in layers, like tubes within tubes. The posh name for layers is laminar. All the fluid is flowing nicely against each other. Laminar flow. So flow in layers is laminar flow. So flow has layers. Onions have layers. And if you've ever seen Shrek, you'll realise that ogres have layers. Now, a funny thing happens with flow. With fluids, there's a sort of maximum velocity they're going to get to, and it won't go any faster no matter what you do. So, with this one here, just in the middle here, it's at its maximum. It will not go any faster than its maximum, no matter what you do to it. And it slowly builds up to, at the edges, going at 0. I've used this drawing of smoke rising because it's a familiar thing that we're used to. As smoke rises in air, what it does is it makes a tunnel through the air, and then the smoke rises in that tunnel. So smoke rising in air is exactly the same as water flowing in a pipe. Now, as the smoke rises a little bit further, it gets to a Reynolds number of greater than 4,000. In the centre there, it couldn't go any faster. What happens is the rest kind of catches up. Now we have what's called turbulent flow. Now it looks slightly, that's a slightly false impression there because it shows a straight line. In actual fact, it's slightly turbulent along the top there. It's like a whole bunch of racing cars jockeying for position. And that's turbulent flow, where they're all just trying to get the pole position. Now, the thing that's important about turbulent flow is that essentially, across the vast majority of the pipe diameter, all of the flow is about the same. If we go anything, in between laminar and turbulent, we call it transitional. So we have laminar, less than 2,000, that's layers. Turbulent, greater than 4,000, that's all mixed up. And transitional between. By the time we get to 10,000, we say that it's fully turbulent. It's well mixed up at that point. Anything above 10,000, and we're into what's called chaotic. The main thing that characterizes chaotic flow is that some of it goes backwards. Chaotic flow is some flow forward, some flow backwards, and some flow just going around in circles. That's chaotic flow. It's all over the place. It's chaos. So these are the levels we're looking at. We've got laminar flow, turbulent flow, and chaotic flow. If you think that the vast majority of our flow meters are in actual fact volumetric flow meters, and the vast majority of our flow meters are in actual fact measuring velocity, then what comes out of this is if we're measuring velocity and we're measuring velocity in one specific point, if we were to measure velocity on a flow profile which is laminar flow, it would make a difference whether we were measuring, I'll find a better colour than that, whether we were measuring in the middle there or whether we were measuring at the edge. So for that reason, if we've got a flow meter which is actually measuring velocity, the ideal flow profile is turbulent, because with turbulent flow it doesn't matter if you measure in the middle, it doesn't matter if you measure there, it doesn't even matter if you measure there. As long as you're not stupid and try and measure there, you will get a representative flow. So with the vast majority of our flow meters, we try and size the flow meter so that we will be having turbulent flow. Now, I just want to get a couple of calculations out of the way while your brains are still working. The first calculation we have is, I have a tank that contains 5,000 litres. It's flowing out of that tank. Oops, the bloody answer's up there, hang on. There you go. Right, it's flowing out of the tank, and it takes 50 minutes to come out of the tank. So if it's 5,000 litres, it takes 50 minutes to come out. What's the flow rate? That was like a question. 5,000 litres, 50 minutes, so it's flowing at what sort of speed? Okay, I don't know where I got to. I think my microphone died on me. Sorry about that. Can you all hear me now? Smiley faces if you can hear me. I've got my microphone working again. Okay, good. Sorry about that. Right, so the calculations here. Had I spoken to you about these calculations? Right. If we've got 5,000 litres and it took 50 minutes, then it's running at 100 litres a minute. It's an easy calculation, and I hope you all get it correct in the test. Next step is another calculation. Given the flow rate, calculate the velocity. Now, what I always think about is I think about a slice through the pipe. And I think that that slice of water moved from over here to over here in the time interval that I'm given. Now what I have is I have a cylinder of water. If I can work out things like the volume of that cylinder and the length of that cylinder, and I know that that cylinder is 1 minute long, then I can work everything else out. This is the sort of thing we'd need to do if the production people give us a flow rate. The production manager turns around and says, right, we're going to put a new system in, it's going to have a flow rate of 100 litres a minute. And you have to put a flow meter in, and you have to ensure that the Reynolds number is going to be correct for that flow meter so that we get turbulent flow. Step one is you draw a diagram. You always draw a diagram. You put down on the diagram all of the things you know. Aside from anything else, drawing a diagram is a good thing to do if you've got absolutely no idea what to do next. It gives you something to pass the time while you wait for the day shift to arrive. Next step, and this is the important one, you convert everything into meters. You convert everything into meters. If you don't do this, you will mess up. This is where you're going to mess up. So we start with the diameter's 50 millimeters. We convert that into meters, 0.05 of a meter. Next, the flow rate, 100 litres per minute. 100 litres is 1/10 of a cubic metre. We need to convert litres into cubic metres. So 100 litres is 1/10 of a cubic metre per minute. Now we know flow rate is volume swept times the time interval. Volume divided by time, that's what flow rate is. So rearranging that equation, we end up with the volume is the flow rate times the time interval. In our case, we're using a minute as a time interval. So that means the volume is 100 litres, or 0.1 of a cubic metre. Step 3. Calculate the cross-sectional area. Cross-sectional area of a circle is pi r squared. So we calculate pi r squared, 3.142 times r. Don't forget, r is half of the diameter, and we're working in meters. So the cross-sectional area is that 0.00196 square meters. Step 4. Consider the volume swept in one time interval. Now, volume, we know, is 1/10 of a cubic metre. We know that volume is cross-sectional area times length. That's the standard equation for the volume of a cylinder, cross-sectional area times length. So rearranging this equation, we end up with length is volume divided by cross-sectional area. And calculating that out, we come out with 51 metres. What that means is that our original slice travelled 51 metres. I could have done that better, couldn't I? There we go. Travelled 51 metres in 1 minute. If it travelled 51 metres in 1 minute, it's moving at a velocity of 51 metres a minute. Now this might seem like it's all a bit strange, but basically you follow the steps. You make a note of this in your notebook or something, and you just work through step 1, step 2, step 3 and step 4. And what pops out at the other end is a velocity, 51 metres a minute. Okay, now let's go the other way. Given the velocity, calculate the flow rate. This is the sort of thing that the flow meters actually do, because the vast majority of flow meters actually are calculating velocity or measuring velocity, and they're using that to calculate the flow rate. So, similar steps. Step 1, draw the diagram. Same as we did before, just draw the same diagram. Step 2, convert everything to meters and the time interval, which is minutes. So in this case, it's quite easy to convert everything to meters. We just say 50 millimeters, 0.05 of a meter. The velocity is already in meters, so that's no big deal. Then, calculate cross-sectional area. This is exactly the same as what we did last time, no different. Fourthly, we consider the volume swept. Now, since the length is 50 meters, the volume of a cylinder is cross-sectional area times length. Cross-sectional area is 0.00196 of a square meter. The length is 50 meters. So the volume of that cylinder is 0.098 of a cubic meter, which is 98 litres. If 98 litres go past in 1 minute, the flow rate is 98 litres a minute. So, are we all vaguely happy to move on from there? I could have a smiley face or an unhappy face.